Hi, I'm Colin Rice. This is the AAE 340 recap video covering March 30th, focusing on eigenvalues and eigenvectors and their relationship to moments of inertia and products of inertia. For starters, we know the basic equation that relates the angular momentum vector to the rotation velocity vector via the inertia matrix. The two vectors, in general, however, are not parallel. This means that the system must be forced in order to continue rotation. If we pick any axis we wanted for h and omega, we would find that we'd still have to force it in order to continue rotation. In nature, however, this rotation is unforced, so we can conclude that the I vector is actually a scalar.
Hi, my name is Sid, and I'm going to explain how we make the mathematical leap from the inertia matrix to the inertia scalar. There are two possibilities. The first is if the matrix is a diagonal matrix, as in there is rotation about one body axis. In this case, the inertia matrix can be represented as a scalar. The second is by grinding out some math about eigenvectors and eigenvalues. For this method, we equate the known inertia matrix times omega with the scalar times omega. The way to solve this is by finding the eigenvalues of the matrix. The corresponding eigenvectors are called the principal axes and are mutually orthogonal.
Hi, I'm Jinsa, and we'll be doing a little example today. Okay, this is a thin rod example. So from before, we actually have the a diagonal inertia matrix, and we're trying to find the eigenvectors and the eigenvalues. To do this, we'll actually take the determinant of the inertia matrix from before, and then set that to 0. In order to get the true eigenvalue, you'll actually multiply the scalar value, which is m times L squared over 12. So now we'll try to find the corresponding eigenvectors. So we have the inertia matrix. We'll actually subtract that by the eigenvalues we found. Multiply that by the E vector and equate that to 0. Also, we have another constraint where the E vector, the length is actually 1. With both of those constraints, we can actually find the corresponding eigenvector for each eigenvalues. Rinse and repeat, and you can actually find the rest of the eigenvalues. Congrats, now you guys are prepared to find the eigenvalues and the eigenvectors. Happy Monday, or tired, miserable, sarcastic, I don't really care.